Hey, don't click off first. Just hear me out. I have some cool science theories that I would like to share with you. First one is how to make a Hadron enforcer in real life. But first, let's backpedal and see, where did you hear this name first? It was in Guardians of the Galaxy Volume 1, where Rocket says he made a device of his own making called the Hadron enforcer, which can destroy moons. So, how does it actually work? The name Hadron is a category of particles called, they are called hadrons. Well, these are category of particles, either baryons or mesons. Or, yeah, I think that's the correct spelling, mesons. An example of a meson is a pion or a kaon, and an example of a hadron is like a proton or a neutron. Those are baryons. So, for safety purposes and easy in explanation, because with for now I think it's easier to accelerate a proton than a neutron, because a proton is positively charged, which means it can be accelerated using either magnetic fields or electric fields or an electromagnetic field, but you get what I mean. So how does this work? In the movie we see Peter Quill, known as Star-Lord. He launches this projectile containing baryon particles, which we are taking into consideration is a proton. These baryon particles inside a projectile, which hit Ronan, the villain of the movie. But let's skip that part. Let's come back to the science. So, in this projectile, there are hadrons, which we are using an example of a baryon called a proton. So, how many of these particles must be collided, because this thing is called an enforcer for a reason. This name actually originates from a particle accelerator called the Large Hadron Collider here on Earth. So we know that it collides particles, which are protons, to release the energy needed for this weapon to explode and destroy a moon, which will be actually taken into consideration our moon. So let's take hypothetically want to destroy the moon. Not that I actually want to, because the moon is very essential for human survival, I mean our survival. So we take into consideration that destroying a moon means like exploding it, but well, not vaporizing it like Thanos snap vaporizing. No, we mean like destroy it, like the way Thanos did with the Power Stone when he threw it at Tony Stark. That type of destroying. So I'm going to take into consideration the binding energy, the gravitational binding energy of the moon. So gravitational binding energy, the formula, it's 3 gravitational constant squared the mass divided by 5 multiplied by the radius of the moon. If you plug in the gravitational constant, the mass of the moon squared times the radius multiplied by the 5, all in SI units though, sorry for those playing in America. So we get about 1.24 times 10 power 29 joules of energy. To put this gigantic amount of energy into your perspective, the sun outputs about 3.85 times 10 to the power 26 joules per second. This is the power outputted by the sun. This is the energy outputted by the sun per second. So if we divide this with the sun's output energy, we get 323 seconds worth of the sun's output energy. That's about 5 minutes and 24 seconds of the sun's energy let out in an instant. This is the energy that we need to bombard the moon with in order to destroy it, to overcome its gravitational binding energy. So, is it feasible to make a Hadron enforcer using our technology? Well, that's where my theory comes in. I'm going to use a normal matter antimatter theory to make sure we get this amount of energy. So let's take into consideration antimatter. You may ask yourself, what is this antimatter you've been hearing about on the internet? Well, this is like the evil twin of normal matter. Like if we take a proton and an antiproton, the evil twin, when they react or come into contact, they turn into pure energy into something we call pair annihilation. And in order to calculate the energy, we just need to know the masses of the two particles, in which a particle and the corresponding antiparticle just they have the same properties except for the charge and therefore the magnetic moment. So the other quantum numbers check out. So including, well, I don't know if the mass is a quantum number, I didn't look into that, but let's look at the most popular known physics formula that you see printed on charts and normally, which rightfully is related to Albert Einstein. He gave us the mass energy conversion formula, which we all know as E is equals to mc squared. So for the mass, we're going to take both masses because we are taking two particles and turning them into energy directly. So the mass of a proton is actually 1.67 times 10 to the power negative 27 kilograms. So because we need two particles for pair annihilation, we times this by 2. That's the mass. The speed of light is approximately 3 times 10 to the power 8. We square this and multiply it with the mass, we get around approximately 3 times 10 to the power negative 10. I'm gonna say in joules. So this is the energy we get by annihilating a proton and an antiproton. So if we divide the energy needed to destroy a moon with this pair annihilation of proton and antiproton, we get 413 sextillion particles. I don't know if that's the correct spelling, but that's a lot of particles. But since these particles exist in the femto nanometer part of the scale, you might think this is a lot of particles. But if we stack all these particles back to back, like they are touching, in which gluons do not, they will hold together the particles, but because of to overcome the Coulomb barrier and due to the repulsion of positively charged protons and the repulsion of negatively charged antiprotons, it's not possible. But let's say we can pack them close enough in which the volume of one proton or one antiproton is about 1.5 times 10 to the power negative 45 cubic meters. If we multiply this and this, we get nearly approximately 1.03 times 10 to the power negative 6 cubic meters. You'd think it'd be a large space occupied by these particles, but this is just hypothesizing that they could be in contact and they could be squeezed down to that point without including neutrons or antineutrons to get that nuclear binding energy to hold these particles together. But since we're not doing that, because we're just taking the hadrons up protons, and I know the question that you're asking is, we said that we are colliding these particles. Well, we are getting to that part. So this is the volume that it will occupy. So space is not a problem. The projectile can hold these smart particles. But in the design